Ever heard of a material so cool it can practically rewrite the rule book for how we think about electronics?
We're talking about some seriously mind-bending physics.
Get ready, because today we're diving deep, deep into the world of twisted bilayer graphene.
TBG for short.
And let me tell you, we've got a stack of research papers here that are, well, they're about to rock your world.
It's not hyperbole to say that TBG is completely revolutionizing condensed matter physics.
So our mission today, if you choose to accept it, is to decode these seriously complex papers. We're talking aha moments galore. And for those of you who don't speak fluent physics, don't worry.
We gotcha.
We'll keep it nice and jargon-free, I promise. Now, at the heart of all this is graphene, right?
Right.
That one atom-thick wonder material that's like taking the world by storm.
Exactly. Graphene by itself is absolutely extraordinary, but when you take two layers of this stuff and you stack them, but here's the thing, you gotta give them a slight twist.
Slight. How slight are we talking here?
I mean slight. We're talking around 1.1 degrees.
Okay, so we're talking an angle so small I probably wouldn't even notice it. Why is this specific magic angle, as they call it, so crucial?
It's like finding that sweet spot on a guitar string.
Yeah.
You know, that precise twist unlocks like this cascade of really bizarre electronic behaviors.
Bizarre how?
Behaviors that, and I'm not exaggerating here, have the potential to change the world.
Okay, now you've got my attention. So the papers mention something called flat bands that form at this magic angle.
Yeah.
Now, I'm all for a good time, but flat doesn't usually scream exciting in my world. What's so special about these flat bands?
Just imagine a crowded dance floor, like everyone's packed in there, barely able to move.
Just like my kind of nightmare.
That's a flat band.
Yeah.
Electrons in these bands, instead of zipping around all freely, they get stuck.
Stuck?
Yeah. And that close proximity, it forces them to interact, but way more strongly than they normally would.
So it's less about dancing and more about those awkward, close-quarters interactions that make you wish you stayed home.
Exactly. And it's those forced interactions that give rise to, like, TBG's most exciting properties.
Intriguing. Now, one of the things that honestly blew my mind a little bit was that TBG can actually switch between two completely different electronic personalities.
Ah, you're talking about the Mott insulator and the superconductor?
Yeah, it's like TBG has a split personality.
And both sides are pretty fascinating.
Let's start with the Mott insulator. How can a material made entirely of carbon, which is famous for its conductivity, how can it just decide it wants to be an insulator all of a sudden?
It's all thanks to those strong interactions we were just talking about. At this magic angle, the electrons in those flat bands, they basically get, like, too close for comfort.
Too close for comfort.
Yeah, and they start blocking each other's movement, which prevents electricity from flowing. Imagine a traffic jam, but for electrons.
So graphene, which is famous for being an amazing conductor, suddenly pulls a 180 and becomes the opposite just because somebody twisted it at a very specific angle.
It's true.
It's like the universe has a really weird sense of humor.
It does seem that way sometimes.
What makes it even more intriguing is that some of these papers suggest that this Mott insulating state, it might actually be an exotic ferromagnet, meaning it could become magnetic just because of how its electrons are arranged.
It's wild stuff.
Hold on, so we're talking about carbon that becomes magnetic just because we twisted it. This is getting out of hand. Okay, so you mentioned TBG has a split personality. We've talked about the reclusive, potentially magnetic Mott insulator side. What about the other side? What happens when TBG decides to ditch this whole insulator thing?
That's when it transforms into, drum roll please, a superconductor.
Okay, superconductor definitely sounds a lot more exciting.
Right.
Break it down for me. What are we talking about here?
A superconductor can conduct electricity, get this, with absolutely zero resistance.
Come again? Zero resistance.
Zero. Imagine power grids that never lose energy.
Whoa.
Computers that are lightning fast and don't overheat. I mean, the possibilities with this are kind of incredible.
This is feeling very, like, sci-fi. Okay, so we have this material, TBG, that can flip between being an insulator, a potential magnet, and a superconductor.
It's a triple threat.
So what are these researchers saying about how these transformations actually happen? Like, at the atomic level, what's going on here?
They're using some seriously incredible techniques to study these transformations. One of the coolest is scanning tunneling microscopy.
Scanning tunneling micro. Say that again?
STM.
STM.
Which is basically like having an atomic scale fingertip that can, like, feel the surface of TBG.
So they're literally, like, mapping out the arrangement of atoms.
You got it. And they're also using spectroscopy, which analyzes how TBG interacts with light. Think of it like taking TBG's fingerprints, but instead of using those old ink pads, we're using beams of light to understand its energy levels.
So it's like giving TBG a full medical checkup, but instead of stethoscopes and x-rays, we're using atomic scale fingertips and beams of light.
I like the way you think. And these medical tests are revealing some pretty mind-blowing details.
Like what?
For instance, several of these papers point to something called, get ready for it, Van Hove singularities.
Van Hove singularities.
Yeah, they show up in TBG's electronic structure.
Okay, you've officially lost me.
Yeah.
Van Hove singularities sound a bit intimidating, I'm not going to lie. What are those?
Yeah.
And why should I care about them?
Okay, imagine like a concert hall, but with different seating sections, right?
Okay.
In each section, it represents a different energy level within the material. A Van Hove singularity, that's like the wildly popular concert, the one where every single person wants to be in a very specific section.
So it's a sold-out show, but for electrons.
Exactly. And just like those crazy popular concert venues, these Van Hove singularities, they're where all the really interesting physics is happening.
So like the mosh pit, basically, the most energetic part.
It's like the researchers have pinpointed the hottest clubs in TBG, where all the cool electrons are hanging out, and that's where all the action is.
I like it. So how does the magic angle play into all of this?
That's the really remarkable part. The magic angle, it doesn't just create these flat bands.
Okay.
It also pushes those Van Hove singularities we've been talking about closer together, and get this, closer to something called the Fermi level.
The Fermi what now?
And that proximity, that closeness, it's absolutely essential for both the Mott insulating and the superconducting states to emerge.
So the closer they are, the more likely these states are to pop up.
Exactly. It's all about getting those ingredients in the right place at the right time.
So the magic angle is like the ultimate party planner in TBG land, making sure all the right electrons are in the right place at the right time for these wild quantum shenanigans to go down.
Now you're getting it. These Van Hove singularities, they're like crucial ingredients in a recipe. Got to have them in the right proportions, brought together just so by the magic angle, and bam, you get something truly extraordinary.
Speaking of extraordinary ingredients, we got to talk about these Wannier functions that pop up in the papers. I'm going to take a wild guess here and say those aren't recipes for some delicious quantum feast.
Not quite, but I like where your head's at. Think of Wannier functions like sketches, almost. They show us how electrons are actually distributed within that TBG superlattice we've been talking about. Like, they give us a visual, a way to picture those electron hangouts, those campsites.
Okay, so instead of a guest list, Wannier functions are like little maps of the electron campsites. Got it.
Exactly. And what's really cool is that the Wannier functions for TBG, they have this very particular three-peaked shape.
Three-peaked. Okay, what's that tell us?
Well, it suggests there's a ton of overlap between those electron positions. Like, they're really packed in there. And that overlap, that could be a big clue when it comes to understanding why we see hints of ferromagnetism popping up.
So those electrons are really getting up in each other's business, no respect for personal space whatsoever. Maybe that explains why they're so keen on aligning their spins and potentially turning the whole material magnetic.
That's the idea. It's like they're huddled together, these electrons, whispering secrets and deciding which way to spin. High drama.
High drama indeed. But hold on. We've got more players in this quantum saga, right? We got to talk about these Fermi pockets that keep cropping up in the research. What are those? Another electron hangout spot we need to add to our TBG map.
You could say that. Think of Fermi pockets like little pools of water scattered across a lake that's mostly frozen over. They represent small groups of electrons that still have a little bit of freedom to move around, even when the surrounding TBG is in that Mott insulating state.
So it's like finding these little oases of electron activity in the middle of this otherwise frozen electron landscape.
You got it. And those Fermi pockets, they're especially interesting because they weren't predicted by those standard theories we usually use to understand how electrons behave. Their very existence tells us we've still got a lot to learn about TBG and this whole crazy world of strongly correlated electrons.
Okay, so let me see if I've got this straight. We've got this magic angle setting the stage, flat bands creating this electron dance floor, Van Hove singularities acting like those super popular clubs, Wannier functions sketching out these close encounters of the electron kind, and then Fermi pockets offering those little escapes from the norm. It's a lot to keep track of.
It's a wild ride, that's for sure. But all this talk about the weird and wonderful physics of it all.
Yeah, what about the real world?
Right. What can we actually do with all this TBG knowledge? What's the point?
Exactly, that's what I'm wondering.
Well, that's the really exciting part. See, TBG isn't just some theoretical curiosity. It's unique properties. They have the potential to, completely revolutionize fields.
Like what?
I'm talking electronics, computing, even the way we transmit energy. This could be huge.
I knew we were building up to something big here. Okay, so paint me a picture. What could a TBG-powered future actually look like?
Imagine, if you will, a world with computers so fast, so energy efficient, they never even think about overheating.
Okay, now you're speaking my language.
Think about power grids that never lose energy. We're talking transmitting energy across entire continents without a single watt going to waste. Imagine sensors so sensitive they could pick up on the tiniest changes in their environment.
It's like we're on the verge of a technological revolution.
Right.
And all thanks to this teeny tiny twist in a couple of layers of carbon atoms.
It just goes to show you the most groundbreaking discoveries, they often come from the most unexpected places.
And in the case of TBG, it seems like we're only just scratching the surface here.
Oh, absolutely. We've only just begun to unlock TBG's true potential. Who knows what other surprises it has in store for us?
Okay, you've convinced me. TBG is officially the coolest kid on the material science block. But even with all this amazing research, all these breakthroughs, I have a feeling there are still plenty of unanswered questions, right?
Oh, tons. While these papers offer some really incredible insights, they've also kind of opened up this Pandora's box of new mysteries.
Like what?
For example, that whole magic angle thing we keep coming back to.
Yeah.
Turns out it might not be so magic after all.
You're saying the magic angle isn't so magic after all.
Right.
Excuse, spill the tea.
Okay, so it's like that 1.1 degree twist we've been obsessing over. Yeah, that's super important, like crucial even. But get this, the exact magic angle, it can actually, like, shift a little bit.
Shift, like it's not a constant.
Yeah. It's not always exactly 1.1 degrees. There are other things that can nudge it a bit.
What kind of things can mess with the magic?
Well, one thing is strain. Like, if those graphene sheets we've been talking about, if they get, stretched or compressed, even just a tiny bit,
Okay.
it can really mess with those interactions, those delicate electron interactions.
Right.
And that can make the magic angle drift a little.
So it's less like flipping a light switch and more like using a dimmer switch, right?
Yeah.
We're fine-tuning that twist to find the sweet spot.
That's a great way to put it. It's all about finding that perfect balance.
So it's not just about the twist, is it? It's about this whole TBG ecosystem, this delicate dance of conditions and properties. And speaking of details, can you remind us about the tools these researchers are using to study these phenomena? I mean, we're talking about things happening at an insanely small scale.
Oh, absolutely. And they've got a whole toolbox full of incredible techniques like scanning, tunneling microscopy, STM, still a rock star in the field.
Right, the atomic fingertip.
Exactly. It's like having an atomic fingertip that can trace out the contours of those flat bands, even tell the difference between those different stacking arrangements.
Oh, right, the AA, AB, and SP stacking regions we talked about earlier.
Exactly.
So those different stacking arrangements, they're like the topography of the TBG landscape.
Right.
And STM, that's our high-resolution map. What other tools are we talking about here?
Well, there's spectroscopy, another super powerful technique.
Right. TBG's energy fingerprint.
Yeah. It helps us analyze how TBG interacts with different kinds of light.
Okay.
And that tells us a lot about its energy levels and electronic structure. It's like shining a light literally on TBG's personality and seeing how it responds to all those different wavelengths. But these tools, they're not just for, passive observation, right? Researchers are actually manipulating TBG using things like electric fields, magnetic fields.
Exactly. That's where things get really interesting. By applying an electric field, they can actually control how many electrons are hanging out in the TBG.
Okay.
Which means they can basically tune it between those different states, the Mott insulator and the superconductor.
It's like having a volume knob for these quantum phenomena. So cool.
Right. And then magnetic fields add this whole other layer of control.
How so?
Well, you can actually use magnetic fields to bring back those elusive Mott insulating states.
Okay.
Even in cases where they weren't initially there, it's like giving those electrons a gentle nudge and reminding them, hey, you have the potential to be insulators, don't forget. So we've got this amazing material, TBG, and this whole arsenal of tools to explore its bizarre properties that could, let's face it, change the world as we know it. It feels like we're on the verge of something big here.
We are. We're really talking about a whole new era in material science. And with TBG, I don't think we've even scratched the surface.
So what's next for TBG? What are the big, hairy, audacious goals driving this research?
Well, the holy grail, the ultimate dream, is definitely room temperature superconductivity.
Okay, yeah. That would be a game changer.
Imagine a world where energy flows freely, without any loss whatsoever. Computers running at unimaginable speeds, levitation becoming a practical mode of transportation.
Okay, now you're just making me dizzy with excitement.
Hmm.
But even if that room temperature superconductivity thing doesn't quite pan out, it seems like TBG still has a lot to offer.
Oh, absolutely. TBG is this incredible platform for developing the next generation of electronics, ultra-efficient transistors, sensors that are ridiculously sensitive, even new platforms for quantum computing.
So not only could TBG change how we power our world, but it could revolutionize how we process information, how we interact with the world around us.
Precisely. And maybe even more importantly, all this research, it's really pushing the boundaries of what we know about matter itself. Who knows what other discoveries are waiting for us out there?
Well said. This has been an incredible journey into the world of twisted bilayer graphene, a material that, let's be honest, seems like it was ripped straight out of science fiction. Every twist, every turn reveals a new wonder, a new possibility.
And the most exciting part is we're only just getting started. The future is looking very bright, and I can't wait to see where this wild ride takes us next.
Well said. To all our listeners out there, we hope this deep dive has left you with a sense of wonder about the material world and all the mind-blowing possibilities hidden within it. Until next time, keep exploring, keep those questions coming, and keep those brains twisting.
I would have been on top of the charts, but it's politics. You do some gimmick shit and post, you get a lot of clicks. Drop some real shit and they probably won't acknowledge you.